Welcome! In this session, we'll be tackling LeetCode problem number 1816, titled Truncate Sentence. We'll explore the problem requirements, break down the solution step by step, and analyze its efficiency. Let's get started. In this problem, you are given a sentence S made up of words separated by spaces, and an integer k. The goal is to return a truncated version of the sentence that includes only the first k words. A word here is defined as the longest possible sequence of non-space characters. The sentence itself does not contain any leading or trailing spaces, and the words are separated by exactly one space. For instance, if S is a string of length between 1 and 10,000 characters, and k is an integer between 1 and the number of words in S, you need to extract and return the first k words from S as a single string. To make this clearer, let's look at some examples. In the first example, the input sentence is "Hello, how are you doing?" and k is 3. The sentence contains 5 words: hello, how, are, you, and doing. Since k is 3, we take the first 3 words, which are hello, how are, and return them as the output. In the second example, the input is "What is your name?" with k equal to 2. This sentence has 4 words, and the first 2 are "what is." So, the output is "what is." Similarly, in the third example, the sentence is "Coding is fun," and k is 1. Here, the first word is coding, which becomes the output. These examples illustrate how to extract the desired number of words based on the value of k. Now, let's consider the constraints and edge cases. The length of the input string S can range from 1 to 10,000 characters, and it only contains uppercase and lowercase English letters along with spaces. Words are always separated by a single space, and the sentence has no leading or trailing spaces. The integer k satisfies the condition that it is at least 1 and at most equal to the number of words in S. For edge cases, if the sentence consists of just one word, for example, S equals word with k equals 1, the output should simply be that word. If the sentence reaches its maximum length of 10,000 characters, the solution must still handle it efficiently. Additionally, if k equals the total number of words in the sentence, the entire sentence should be returned. Finally, the solution must account for case sensitivity, ensuring mixed case sentences are handled correctly, such as S equals hello world with k equals 2, which would produce hello world as the output. When solving the problem of truncating a sentence, the first approach we can consider is using a brute force method that leverages Python's split and join functions. The idea here is straightforward. Since the sentence is essentially a series of words separated by spaces, we can break the input string S into a list of words using the split method. Once we have the list, we can easily isolate the first k words by slicing the list. Finally, we use the join function to reconstruct the truncated sentence by joining these k words back into a single string. This approach is simple to implement and makes use of Python's built-in methods, which are both efficient and easy to read. However, it comes with a trade-off. While the time complexity is O(n), since we process the entire string once to split it, the space complexity is also O(n), because we create an intermediate list to store the words. This additional space usage may not be ideal in scenarios where memory is constrained, but it does offer clarity and ease of implementation, making it a strong candidate for many use cases. Another approach we can explore is an optimized solution using a two-pointer traversal technique. This method avoids the extra space required by the brute force approach and instead processes the string character by character. The key idea is to count spaces as we traverse the string, which allows us to determine when we've encountered the first k words. To implement this, we initialize a counter to track the number of spaces and an index to iterate through the string. As we traverse the string, we keep counting spaces until we reach the kth word. At this point, we can slice the string from the start up to the current index, giving us the truncated sentence. This approach has a time complexity of O(n), as it only involves a single traversal of the string, and it achieves an impressive space complexity of O(1), since no additional data structures are required. However, while it's more memory efficient, it's slightly less intuitive than the split approach and introduces some complexity in implementation. For developers who prioritize performance in memory-constrained environments, this method provides a valuable alternative. A third approach involves using regular expressions to directly extract the first k words. This is a compact solution that leverages the power of regex to match and capture the required portion of the sentence. While this method can be concise and elegant, its readability and maintainability are often reduced, especially for developers who are less familiar with regex syntax. Additionally, the time complexity of this approach typically depends on the regex engine but is generally O(n). While it avoids the verbosity of other methods, debugging regex-based solutions can be challenging, and they may introduce unnecessary overhead for simpler problems like this one. After evaluating these three methods, the brute force approach using split and join emerges as the preferred strategy. It strikes a balance between simplicity, readability, and efficiency, achieving a time complexity of O(n) that aligns well with the problem's constraints. While the two-pointer approach is more space-efficient, its added complexity makes it less appealing unless memory usage is a critical concern. Regex, on the other hand, is avoided due to its reduced clarity and potential for overcomplication. By choosing the split and join method, we ensure the solution is both practical and easy to understand, making it an excellent choice for this problem. Let's begin by understanding the problem. We are given a sentence S, which is a string of words separated by single spaces, and an integer k. The goal is to return the first k words of the sentence as a single string, preserving the order of words as they appear in S. To achieve this, we can use a brute force approach that leverages Python's built-in split and join methods. First, we parse the input sentence into a list of words. This is done using the split method, which breaks the sentence into individual words based on spaces. For example, if the input string is S equals the quick brown fox jumps, calling s.split will give us the list, the quick brown fox jumps. This step simplifies the problem by allowing us to work with the words directly as list elements, making it easier to manipulate them in subsequent steps. Now that we have the words as a list, the next step is to extract the first k words. This is accomplished using Python slicing syntax, which allows us to create a sublist containing only the first k elements. For instance, if k equals 3 and the list of words is the quick brown fox jumps, slicing with words k will give us the sublist, the quick brown. This operation is efficient, with a time complexity of OK, because it directly accesses the required portion of the list. Additionally, Python handles edge cases like k being greater than or equal to the total number of words gracefully. In such scenarios, the slicing operation simply returns the entire list without raising any errors. Finally, we move on to reconstructing the truncated sentence from the selected words. To reconstruct the truncated sentence, the selected words need to be combined back into a single string. This is done using the join method, which takes a list of strings and concatenates them with a specified delimiter, in this case, a space. For example, if the truncated list of words is the quick brown, calling.join, truncated underscore words, will produce the string the quick brown. This operation is also efficient, with a time complexity of OK, as it only processes the selected words. Once the string is reconstructed, it is returned as the final output. For example, given the input S equals the quick brown fox jumps and k equals 3, the output would be the quick brown. This straightforward approach is both simple to implement and efficient for this problem. To understand why this approach is effective, let's consider the data structures used. First, the list of words allows for efficient slicing and joining operations. By splitting the sentence into a list, we can isolate and manipulate specific segments of the data without modifying the original string. Next, the use of strings ensures that the final output is properly formatted and immutable. The combination of these two structures enables the algorithm to handle the problem efficiently. Specifically, the slicing and joining operations are highly optimized for lists in Python, ensuring that the algorithm remains performant even as the input size increases. This balance of simplicity and efficiency makes the chosen data structures ideal for solving this problem. Let's walk through a concrete example to solidify our understanding. Suppose the input is S equals the quick brown fox jumps and k equals 3. First, we split the sentence into a list of words. Words equals s.split results in the quick brown fox jumps. Next, we extract the first k words using slicing. Truncated underscore words equals words k, which gives the quick brown. Then, we join these words back into a single string using .join, truncated underscore words, resulting in the quick brown. Finally, this string is returned as the output. While the current approach is already optimized for most cases, there are opportunities for further optimization, such as streaming the string to reduce memory usage. However, these alternatives often come at the cost of increased code complexity, making the current solution a practical and efficient choice for most scenarios. The provided Python implementation solves the problem of truncating a sentence to its first keywords. Here is a detailed explanation of the code. 1. Class definition. The solution class is declared, which contains the method truncate sentence. This is a common structure for LeetCode problems. 2. Function input. The method truncate sentence accepts two parameters. S. A string representing the sentence where words are separated by single spaces. K. An integer indicating the number of words to retain from the sentence. 3. Splitting the sentence. The split method is called on the string S to break it into a list of words based on spaces. For example, if S equals hello world this is Python, the result of S.split will be hello world this is Python. For selecting first keywords, using slicing, words K retrieves the first keywords from the list. For instance, if K equals 3, the slicing will result in hello world this. 5. Joining words. The join method is used to concatenate the selected words back into a string, with a single space as the separator. For example, .join, hello, world, this, results in the string hello world this. 6. Return statement. The final truncated string is returned as the output. Edge cases. If K is equal to the total number of words in the sentence, the entire sentence is returned. If S is empty, the split operation results in an empty list, and the function returns an empty string. This solution is efficient with a time complexity of O(n), where n is the length of the input string S, as splitting and joining are linear operations. It is simple and handles all edge cases effectively, matching the requirements of the problem statement. This is the Java implementation of LeetCode problem number 1816, truncate sentence. The logic is identical to the Python version. The input string is split into an array of words, and the first keywords are joined back together. Key differences include the use of Java's string.split method, a string builder for efficient string concatenation, and Java's type declarations. The solution ensures concise and clear implementation while leveraging Java-specific features. In this example, we are given the string S as hello how are you and an integer k with a value of 3. To begin, the split method is applied to the string S, which breaks it down into a list of individual words. This results in the list, hello, how are you? At this point, we have an intermediate state where the words are separated. Next, we use slicing to extract the first keywords from the list. Since k is 3, the slice words 3 gives us the sublist, hello, how are. Finally, we use the join method to combine these words back into a single string. By joining them with a space separator, we produce the final output, hello how are. This demonstrates how the sentence is truncated to the first 3 words in just a few simple steps. Now, let's look at another example where the string S's LeetCode is fun and k is 4. First, the split method is applied to the string, converting it into the list, LeetCode is fun. Here, the intermediate state shows the words broken down into a list. Next, we perform the slicing operation words k. Since k is 4, which is greater than the total number of words in the list, the entire list is returned as is, LeetCode is fun. This means no words are excluded because k is large enough to encompass all the words available. Finally, the join method is used to reassemble the words into a single string. By joining the words with spaces, the result is LeetCode is fun. This example illustrates that when k is greater than or equal to the total number of words, the entire sentence remains intact. In the final example, the string S's truncate this sentence and k is 1. As before, we start by applying the split method to the string, which breaks it into the list, truncate this sentence. This gives us an intermediate state where the sentence is separated into its individual words. Next, we use the slicing operation words, k, to extract the first keywords. Since k is 1, only the first word is selected, resulting in the sublist, truncate. Finally, we use the join method to combine the selected word back into a single string. Joining this single word with a space separator produces the final output, truncate. This demonstrates how the method works when truncating the sentence down to just one word. In this problem, we analyze the time complexity by breaking down the key operations. First, we have the split function, which processes the entire string S to separate words by spaces. This requires a complete traversal of the string, so its time complexity is O, n, where n is the length of the string. Next, we use slicing to extract the first k words, which takes O, k, time because it involves copying references for the first k elements. Finally, the join operation concatenates the selected words into a new string. The time required for this depends on the total number of characters in the first k words. In the worst case, if all words are of similar length, this operation will also scale linearly with the length of the input string, resulting in an O, n complexity. Together, these operations give us a detailed view of how the time cost is distributed. Now, combining these steps, the overall time complexity is the sum of O, n for splitting, O, k for slicing, and O, n for joining. Since k is always less than or equal to n, the O, k term is overshadowed by the O, n terms. Therefore, the overall time complexity simplifies to O, n. Shifting to space complexity, the split function creates a list where each word is stored as a separate element. If the string contains m words, the space required is proportional to the total number of characters in the string, which is O, n. For slicing, a new list is created to hold references to the first k words, requiring O, k space. This additional space is relatively small compared to the O, n space from split, so it's less significant in the overall calculation. Additionally, the join operation creates a new string to hold the final result. The space required for this string is proportional to the total number of characters in the first k words, which is at most O, n. When we combine these components, the dominant space usage comes from the list created by split, and the final result string from join, both of which require O, n space. The slicing operation adds only O, k space, which is negligible when compared to O, n. Thus, the overall space complexity is O, n. To compare, a naive approach might involve manually iterating through the string and counting spaces to locate the first k words, then slicing the string directly. This would still require O, n, time for traversal and O, n, time for constructing the result string, leading to a total time complexity of O, n. However, this approach is less efficient and more prone to errors. The optimized approach used in this solution leverages Python's built-in split and join methods to achieve the same result more cleanly and efficiently. Both the naive and optimized approaches share the same time and space complexity of O, n, but the current solution benefits from the optimization and readability of standard library functions. Lastly, the time and space complexities remain consistent across the best, average, and worst cases. This is because the operations of splitting, slicing, and joining all scale linearly with the size of the input string, ensuring that the complexity is always O, n, regardless of the input characteristics. When solving the truncate sentence problem, there are several common pitfalls to watch out for. First, failing to handle edge cases can lead to runtime errors. Examples include empty strings, strings without spaces, or when the value of k exceeds the total number of words. It's crucial to explicitly test your code against these scenarios. Another mistake is incorrect indexing during slicing. For instance, in Python, slicing with words k excludes the upper bound, so overlooking this can cause off-by-one errors. Developers may also inadvertently modify the input string directly, which can create unintended side effects, especially if the original string is used elsewhere. Inefficient splitting is another issue, such as repeatedly splitting the string inside loops, which unnecessarily increases the time complexity. Instead, split the string once and reuse the result. Finally, overcomplicating the solution by using unnecessary data structures or algorithms can make the code harder to debug and maintain. Stick to simple string and list operations for clarity and efficiency. In interviews, understanding patterns in string manipulation can significantly improve your problem-solving approach. Many string-related problems, including truncating a sentence, rely on operations like splitting, joining, or scanning the input. Recognizing these patterns allows you to apply similar strategies to variations of the problem. It's also important to be aware of trade-offs in your approach. For instance, while brute force solutions like repeatedly concatenating strings may work on small inputs, they often fail on larger test cases due to poor scalability. Always evaluate how well your solution handles larger datasets. Additionally, interviewers often expect you to discuss spacetime complexity. For example, splitting a string has a time complexity of O(n), and also uses O(n) space. Finally, proactively discussing edge cases during an interview demonstrates thoroughness and critical thinking. By highlighting potential issues in your approach to handling them, you convey a deeper understanding of the problem. The truncate sentence problem shares similarities with several other LeetCode problems, making it a great opportunity to build transferable skills. For instance, in LeetCode 58, length of last word, you're tasked with finding the length of the last word in a string, which involves splitting or scanning techniques. LeetCode 151, reverse words in a string, requires reversing the order of words, which is another variation of word splitting and joining. LeetCode 186, reverse words in a string 2, takes this further by reversing words in place, focusing on space optimization. And LeetCode 68, text justification, is a more advanced problem that involves manipulating words to format text within a specific width. As for alternative approaches, the brute force method is the most straightforward. You split the string into words, take the first k words, and join them back. This approach has a time complexity of O(n) and a space complexity of O(n), making it simple and effective for most cases. Another approach to solving this problem is the two-pointer technique. Here, you traverse the string character by character, counting spaces to track the number of words until k words are reached. This method has a time complexity of O(n) and a space complexity of O(1), as it avoids creating additional data structures like a list. However, it's more challenging to implement and debug compared to the brute force method. An alternative is using a regex-based approach. Regular expressions can extract words from the string, allowing you to join the first k words. While the time complexity remains O(n), depending on the regex engine, and the space complexity is also O(n), this method introduces added complexity. Additionally, regex may not be the best choice in all cases due to its dependency on the regex library and the potential for more intricate debugging. Each of these approaches has trade-offs, so choosing the right one depends on the problem constraints and your familiarity with the techniques. Great job! To summarize, we tackled the truncate sentence problem using a straightforward brute force approach with string manipulation. This method is efficient for the given problem constraints, with a linear time and space complexity. Remember, mastering string manipulation techniques is crucial for solving similar problems efficiently. Thanks for joining, and don't forget to like, share, and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!